So this is the week 12 screencast reflections, and I wanted to spend a little time talking about the reading that we were asked to do, and that was from the Sherwood and Chabay textbook reading. And it kind of started out interesting because it was, I guess, not starting in a introductory section, and so it kind of took me a little while to wrap my head around it, but it's been a while. And so, kind of got used to some of the terminology and such. It's interesting also in the notes for unit 4, kind of making the analogy between the electric field, and the gravitational field, and the magnetic field, symbolized by B. Not sure why that's symbolized by B, but anyway, as the ratio, I guess, between magnetic force to the product of charge times velocity. So really, it's the full magnetic force from moving charge, as opposed to the electric force, which is electric force per stationary charge. So anyway, so that was useful. Then it got quickly into current loops and looking at this idea of magnetic dipole moments. And the moments, an interesting idea how moments seems to be in general a combination of a physical quantity and a distance. And so I guess for the moment, for the magnetic dipole, it's equal to the product of current times the area of the loop, and that's pi r squared. And so one question I had is, so this causes rotation, I guess, the moments. And so for here, for example, on the bottom of page 725 in the reading, we can go ahead and predict the direction of the magnetic force on a magnetic dipole from the magnetic field created by the loop of current. But then it seems that the direction of the magnetic the magnetic field, as well as the magnetic dipole moment, it is in line with each other. And so what exactly does that mean? I guess if you would have some sort of another magnet, a compass needle, say, in the vicinity of the magnetic field created by this loop of wire, then it would cause that compass needle to deflect, it seems, and move. I guess some of the wording and the questions in the reading were a little confusing. For example, it seems that the magnetic moment it relates to the torque on an object from an externally applied magnetic field. And so I guess that torque would be applied to another magnet placed in the current, the loop of current, that magnetic field. So it's not basically the way that the loop of wire is going to be deflected, but it's going to be another external magnet, how that would be deflected. So that was a little confusing about which is which. But then later in the chapter, it talked about how the loop of wire would actually be deflected, and you could actually do an experiment in the question section where you could show that the wire is deflected if placed in some sort of a magnetic field, such as the Earth's magnetic field. So anyway, that was a little confusing. I also wondered, why do the magnetic fields form closed loops? I guess that was never given a mechanism for that. It was kind of more or less stated how that, it's different from the electric field, but there was no, I guess, rationale for it. And an interesting thing in modeling in general is, well, the reason I like it so much is because it does provide mechanisms and real microscopic kinds of reasonings for why things occur as they do. But here in the magnetism, at least in the first sort of introductory modeling materials here, like Lab 1, Lab 2, they don't necessarily get at why the magnetic field forms a closed loops. Also, I guess, in teacher's notes, in the introduction of the teacher's notes, it talks about magnetic flux, which seems to be related to the strength of magnetic field, which also is a bit confusing. And I'm not sure how much, I guess, the modeling materials get into that, because there is some terminology, to this. You got magnetic flux, you got moments. And so that's, a little bit confusing. And let's see, another thing I wanted to bring up is that, so it was a little confusing to me that the electric field and the magnetic field, the electric field for a current in a wire, as well as the magnetic field produced by a closed loop, say, it is not following an inverse square law, but it's actually following, at least the magnetic field is following an inverse relationship that varies by the cube of the radius, the distance between two magnets. And so that was interesting. And then, I went back and didn't really understand why it's not an inverse square law, but it seems that the inverse square law applies to the electric fields around a point charge. But around a current carrying wire, then that the inverse relationship varies by the cube or even the fifth root of the distance between two objects. And so then I guess we got into cross products, which I had to revisit, and the cross products were something that I've studied before, but I guess I don't fully understand how they came up with this idea of how the cross product, the straight wires contribute nothing to the magnetic field at A, because for each wire, the cross product between, I'm assuming this is the length of the wire times the radius, that doesn't make any sense, equals 0. So I don't understand exactly why, looking at this example problem, why straight wires do not contribute anything to the magnetic field. And I'm also a little confused about how they get use the cross product of the change in length times the radius to get the magnetic field. Then it got into angular momentum as well, and I like the idea of how it's connecting lots of these general physics principles, and applying it to how it fits in with magnetic phenomena. But again, it's an area of confusion. And again, this uses a cross product idea, how the angular momentum is equal to the product between the position times the momentum. And so I saw that there was an experiment mentioned on page 731 of the reading. And that was a way to go ahead and show how a moment is produced by a magnetic field, and what that would do, for example, to a compass needle, or due to the wire, the loop of wire. Then also, one more thing I want to mention is that disc versus bar magnets, how the disc magnets, they align themselves differently, two disc magnets together versus the two bar magnets together. And I thought that, I'd like to